In this video, we're going to talk about bases. So recall that when we introduced linear combinations of vectors, we did so by thinking about a set of vectors, v1 down to vn, as a set of directions that we can use to move through Rm. So generally, when we think about any sort of space like R2 or R3, where we can visualize things, or more generally, Rm, we use the standard set of instructions, E1, E2, down to Em. One reason why it's nice to use these instructions is there's an easy way to represent any point in Rm as a linear combination of these vectors. That is, for any point x1, x2, down to xm in Rm, we can always think about this point as corresponding to the vector x1 e1 plus x2 e2 plus etc. plus xm em, which is the vector whose coordinates are x1, x2, down to xm. And of course, this corresponds to what we learn all the way from elementary school about how to locate points in, say, the plane. The vector e1, for example, whose coordinates are 1 and 0, corresponds to the usual x-axis, and the vector e2 correspond to the y-axis. So just like in elementary school, if you want to locate a point x, y, you can move x times e1 units along the x-axis, and then move y times e2 units along the y-axis. So while this standard set of instructions is familiar, as we'll see later on, it's sometimes convenient to use a different set of vectors. So we're going to define a set of vectors, v1, v2 through vn in Rm, to be a basis for Rm if two things. One, the span of those vectors is equal to Rm, just as for the vectors e1 through em, and the vectors v1 through vn form a linearly independent set of vectors. So, two quick observations about this. Number one, if the span of these vectors is going to be all of Rm, then the matrix with columns v1, v2, down to vn must have a pivot in each row. This tells us that our matrix must have at least m columns, since there are always going to be m rows, and there cannot be more pivots than there are columns. Our second observation is if these vectors are linearly independent, then the matrix with columns v1 through vn must have a pivot in every column. Since we know that there are m rows and the number of pivots cannot exceed the number of rows, this tells us that the number of columns is bounded above by m. Now, we've seen by observations 1 and 2 that n is an integer which is at least as large as m, but no larger than m. This tells us that n must in fact be equal to m. This tells us that any basis for Rm must have exactly m elements. Now, to go back to our introduction to Rm, we recall that we called it m-dimensional space. And we thought about this as m-dimensional space because there were m different directions given by the vectors e1, e2, down to em. So going back to R2, the direction e1 corresponds to our x direction, the vector e2 corresponds to our y direction. If we throw in a third dimension, R3, then e1 corresponds to the x direction still, e2 to the y direction and e3 to the z direction. If our bases are supposed to be generalizations of these vectors, then it shouldn't be surprising that any basis should have this many elements. In fact, this is the proper way to define the notion of dimension. So now that we have a definition for a basis, and we know that the dimension of a space is defined by the number of elements in a basis, then it would be nice to know how to identify whether or not a set of vectors form a basis. And this is where our dimension, or our observation about the size of a basis, comes into play.